Hey everyone, I hope you're having a great day. My name is Jonathan Rocha, and let's dive deep in a topic in machine learning that is rarely discussed in detail and is long overdue: persistent homology. So, without further ado, let's jump right in. All right, consider these two data sets. If I asked you to describe them statistically, their means, variances, and covariances, you'd find nearly identical numbers. A principal component analysis would give you the same eigenvalues. Yet these datasets are fundamentally different. The one on the left has a hole, the one on the right does not. This distinction, the presence of or absence of topological features like connected components, loops, and voids, is invisible to traditional statistical summaries. Persistent homology gives us the mathematical machinery to detect, quantify, and leverage these features. So, what does topology actually capture? It studies properties that are preserved under continuous deformation, stretching, bending, twisting, but not tearing or gluing. The classic example: coffee mug and a donut. They are topologically equivalent because one can be smoothly deformed into the other. Both have exactly one hole. We quantify these features with beta numbers. Beta 0 counts connected components, how many separate pieces. Beta 1 counts loops or one-dimensional holes, cycles that can't be filled in. And beta 2 counts voids or two-dimensional cavities, enclosed hollow spaces in 3D. For machine learning, the invariance of these features is a strength. They're robust to exactly the kinds of perturbation we encounter in practice: sensor noise, sampling variability, and measurement error. But here's the challenge: our data are finite point samples, not continuous surfaces. How do we extract topological information from a discrete set of points? The answer depends on scale. Look at this figure. At a fine scale, every point is its own connected component. Nothing is connected. At a coarse scale, everything merges into a single blob. The mathematical insight of persistent homology is to track topological features across all scales simultaneously and retain only those that persist. That's the key idea. Let's now build up the math. We start with the combinatorial scaffolding, the simplicial complex. A K-simplex is the convex hull of K plus 1 points. So, a zero simplex is just a vertex, a point. A one simplex is an edge, a line segment between 2 points. A two simplex is a filled triangle, 3 points, and everything inside. A three simplex is a filled tetrahedron. A simplicial complex, K, is a collection of simplices that is closed under taking faces. That just means if a triangle is in K, then all of its edges and all of its vertices must also be in K. Nothing dangling. So, to detect topological features algebraically, we define the boundary operator, partial K. The boundary operator is a linear map from K chains to K minus 1 chains. It's defined on a K-simplex sigma equals the ordered set V0 through Vk by partial k of sigma equals the sum over I of negative 1 to the I times the simplex with Vi removed. The hat means omit that vertex. Let me show the example for a triangle. The boundary of the triangle V0, V1, V2 equals the edge V1, V2 minus the edge V0, V2 plus the edge V0, V1. So the boundary of a filled triangle is its three edges with alternating signs. Now, here's the fundamental property, the single most important fact. Partial k minus 1 composed with partial k equals 0. The boundary of a boundary is always 0. You can verify this by expanding the double sum. Every face appears twice with opposite signs, so they cancel. This property is what makes homology possible. Now, with that property in mind, we can define homology. The kth homology group is hk of k equals the kernel of partial k, modulo the image of partial k plus 1. Let me unpack that. The kernel of partial k, that's everything that maps to 0 under the boundary operator. These are called k-cycles, chains with no boundary. Think a loop of edges that closes on itself. The image of partial k plus 1, that's everything that is the boundary of something higher dimensional. These are called k-boundaries. Homology is the quotient, cycles that are not boundaries, a loop that isn't the edge of any filled region. That's a genuine whole. The rank of hk is the kth beta number. So beta k equals the rank of hk. Beta 0 counts connected components, beta 1 counts independent loops, and beta 2 counts enclosed voids. Now we connect this to the point cloud data. Given a finite set of points x in Rn with some distance metric d, we build the Vittorius-Rips complex at scale epsilon. Vr epsilon of x is the set of all simplices x0 through xk such that distance between every pair x to the I, xj is at most epsilon. A simplex is included if and only if all pairwise distances are at most epsilon. As epsilon grows from 0 to infinity, we get a nested sequence. The empty set equals Vr0, contained in Vr epsilon 1, contained in Vr epsilon 2, and so on up to Vr infinity. This nested sequence is called a filtration. Applying homology to each complex and tracking how features appear and disappear is precisely persistent homology. Each feature has a birth time and a death time. The persistence is the lifetime. So the persistence of feature I equals the death time minus the birth time. All right, here are the persistence diagrams for our two motivating datasets. Each point represents a topological feature. Its x-coordinate is its birth time, and its y-coordinate is its death time. Look at the annulus on the left. See the single orange point far from the diagonal? That's the persistent loop, the true hole in the data. It was born early and died late. That's signal. All the points clustered near the diagonal, those are short-lived features, noise. They appeared briefly and vanished. So now look at the cluster on the right. All the H1 features are near the diagonal. There's no persistent loop because there's no hole. The persistence diagram captures this distinction cleanly. The rule of thumb, far from the diagonal means persistent, which means signal. Near the diagonal means ephemeral, which means noise. So here's an equivalent visualization. The persistence barcode. Each feature is a horizontal bar running from its birth time to its death time. Long bars are signal. Short bars are noise. In the annulus barcode, you can see one very long red bar in H1. That's our loop. In the cluster, all the red bars are short. No persistent topology. Now for the most important result in applied persistent homology, the stability theorem, proved by Cohen, Steiner, Edelbrunner, and Herrer in 2007. The theorem states that persistent homology is Lipschitz continuous. The bottleneck distance between the diagram of F and the diagram of G is at most the L infinity norm of F minus G. In plain terms, if your data has measurement noise bounded by some delta, then your persistence diagram shifts by at most delta in bottleneck distance. So why does this matter for machine learning? Three reasons. If noise is bounded by delta, diagrams shift by at most delta, guaranteed. This is a hard mathematical guarantee, not a statistical one. It holds for every dataset, not just an expectation. It's what makes TDA viable for real-world noisy data. And here's the empirical verification. I took a clean point cloud sampled from the circle, added increasing amounts of noise, and measured the bottleneck distance between the original and perturbed persistence diagrams. Every single observed point lies below the diagonal, exactly as the theorem predicts. The bottleneck distance never exceeds the L infinity norm of the perturbation. So persistence diagrams are powerful, but they live in a non-Euclidean space. They're multi-sets of points. Most ML algorithms expect fixed-length vectors, so we need vectorization methods. Persistence images, introduced by Adams and colleagues in 2017, solve this elegantly. The pipeline is as such. Transform each point from birth-death coordinates to birth persistence coordinates. We go from B comma D to B comma D minus B. Place a Gaussian kernel at each transformed point. Weight by a function of persistence, so more persistent features get more weight. Discretize onto a grid. The result is a fixed size matrix, literally an image, that can feed into any ML pipeline. And crucially, persistence images are stable. Small changes in the diagram produce small changes in the image. So here's where persistent homology connects directly to time series analysis. Given a scalar time series x of t, Topkin's delay embedding theorem says we can reconstruct the topology of the underlying dynamical system. The embedding maps each time point to a vector. X of t maps to the vector x of t plus tau, x of t plus 2 tau, and so on up to x of t plus d minus 1 times tau. Look at the three rows here. A periodic signal, a clean sine wave, produces a point cloud that looks like a circle. The persistence diagram shows a single strong H1 feature far from the diagonal. That's the loop. A quasi-periodic signal produces a more complex attractor. And white noise? Just a blob. No persistent topology. This is the key insight from Perea and Herrera in 2015. Periodic signals produce persistent loops. Chaotic signals produce complex signatures. And regime changes, transition between behaviors, shows up as shifts in the persistence diagram. So, putting it all together, I generated 150 time series across three dynamical regimes: periodic, quasi-periodic, and chaotic. Extracted 10 topological features from H0 and H1 persistence diagrams, and trained a random forest classifier. Five-fold cross-validation accuracy, over 90%. Topological features alone, no traditional time series features, successfully distinguish dynamical regimes. So the feature importance chart shows that both H0 and H1 statistics contribute meaningfully. All right, so three quick frontiers worth knowing about. First, differentiable persistence. Recent work has shown that persistence diagrams can be made differentiable almost everywhere, enabling topological loss functions for end-to-end deep learning. Second, persistent homology on graphs. By constructing filtrations on graph structures, we can compute topological signatures that complement GNN features. And third, computational scalability. The Ripser algorithm by Bauer in 2021, which with implicit matrix reduction, has made TDA practical for datasets with tens of thousands of points. So I'll close with Carlson's words from his foundational 2009 paper, Data Has Shape and Shape Matters. Persistent homology provides the ML toolkit with genuinely new, provable, stable topological features that capture structure invisible to traditional statistics. The mathematical foundation, simplicial complexes, boundary operators, homology groups, filtrations, and the stability theorem is rigorous, beautiful, and practically powerful. So with that, thank you very much for exploring persistent homology with me. It's been a lot of fun. If you'd like to learn more about persistent homology, visit my new website, formalml.com, where I've put together an in-depth article on this very topic and others with interactive charts that explain this key aspect of machine learning in great detail. The link is on your screen, so feel free to check it out. If you have any questions, scan the barcode to send me an email. I'm happy to help. Thanks again and have a fantastic day.